So welcome everyone to Introduction to Databases Part 1. There will be a Part 2 in this series, and that's next week with my colleague Ryan Horn. I'll talk a little bit more about that later, but please take a look for that if you haven't seen it already. If you like this introduction, you may also like that one as well. So a little bit about me. I'm Francesca Albrezzi. I'm in the Office of Advanced Research Computing here at UCLA. I've taught for the Digital Humanities program and in World Arts and Cultures / Dance, which is actually the program where I did my dissertation. I'm the editor-in-chief and director of the virtual gallery for the International Journal of Digital Art History. I currently co-chair the educational committee for the College Art Association, and affiliated with a number of wonderful other professional organizations. Really, my expertise is in extended reality technologies and digital humanities broadly. So I'm really excited to get to talk with you today about databases, which are such a important research infrastructure and method, particularly when we're thinking about how we care for assets. So coming out of the museum world, database understanding database management is a really, really important thing. So in this workshop, we're going to cover core database concepts and some examples of applications in research and real world scenarios. Again, this is an introduction. If you've never really dealt with databases before, never really thought about databases before, we'll be starting from sort of the very ground level. So think of this really as a beginner's introduction. I'll start with a historical interview to give us, or a historical overview of developments of databases, just to give us some context. And then I'll introduce various types of databases. So we can talk about which database type you might choose depending on the work that you're doing. We'll cover concepts like collections management and tables and data types, and think about really critical principles of database design, including normalization and schema creation, especially when moving from flat to relational databases, because I think that's where typically when we're talking about intro work in databases, we're often thinking about how do we migrate away from a spreadsheet that I've created for my research and really make it more robust using something like a relational database. The workshop will also introduce SQL, covering sort of fundamental commands and queries. Again, it'll get your feet wet. We won't be setting up our own SQL environment. So if you were looking for that, we just don't have enough time to get into that today. But you'll understand by the end of this how sort of SQL database tools operate, so that you can get started. And we'll discuss how to choose the right database platform for different projects, and also think about sort of some ethical considerations and challenges related to things like legacy data and access, right? Whether people should always have access into what kinds of data, right? And that's what databases can really be helpful for too. And then we'll wrap up. I'll provide some additional resources, and we can have some time for discussion or questions. I also want to mention that the majority of the information I'm sharing today comes from Johanna Jucker's Digital Humanities coursebook, which is just a great resource for digital methods for research and scholarship in general. So again, if you're looking for a core resource to ground your work, that's a great place to start. So with that, let's dive into a database overview. Throughout history, spreadsheets and tabular records have been integral in human culture. Obviously, we are fans of making lists, right? It helps us organize, it helps us make sense of the world. However, the concept of the relational database is a much more recent innovation. So this is credited to the computer scientist Edgar Codd, and the relational database emerged in the early 1970s. So Codd's groundbreaking work established the structure of relational databases, highlighting the efficiencies of cross-referencing tables instead of relying on flat or hierarchical arrangements for data. While I was working at IBM, Codd, alongside with his colleagues Raymond Boyce and Donald Chamberlain, developed SQL, which was the precursor to SQL, which is a programming language for database queries. And the major sort of industrial breakthrough came in 1979 when Dan Bricklin and Bob Frankston introduced VisiCalc, which is an application that transformed personal computers into essentially commercial tools by automating spreadsheet calculations. This innovation allowed business projects to, or businesses to project financial scenarios instantly and became an instant success. So that's really what brought it to a large market. Advancements continued with the development of object-oriented databases, which integrate operations and entities, and non-SQL databases like graph databases that support network visualizations. And you'll be hearing a lot about that in part 2 of this workshop series, again, by my colleague, Brian Horn. Remarkably, few new database structures have been introduced sort of since this onslaught, which really I think underscores the robustness and longevity of these data organization methods. So let's make sure that we're all on the same page. Let's define what a database is. Generally, any organized collection of structured information or data stored, typically electronically, and managed by a system that allows easy access, retrieval, and management can be called a database. So that's why even spreadsheets really are considered what we call flat databases, and we'll talk a little bit more about that. But there are a ton of available databases that you probably are already regularly using for conducting research. These big data repositories are indispensable tools that enable researchers to store, access, analyze, and share data across various disciplines. For example, one of my favorites, Project Gutenberg, is a library of over 75,000 free ebooks in different file formats. So it focuses on older works, which are where the US copyright has expired. So all of these things are in the public domain. But like if you were looking to do a text analysis project featuring Victorian literature, this would be a great database resource, right? So we really use databases for all kinds of storage and also to offer access to wider publics. The purpose of a database in research is really multifaceted and essential for effective data management and analysis. So databases, right, help with efficient storage. They provide a structured way to store large volumes of data, making it easier to both manage and retrieve information quickly. Data organization is another reason why you might use a database, right? They help us to organize data systematically, allowing researchers to categorize, label, then sort our data. Also, this helps with accessibility and usability of the data. By enforcing rules and constraints, databases ensure that data remains accurate and consistent, which is crucial for reliable research outcomes. Also, databases support complex queries and data analysis, enabling researchers to uncover patterns or correlations and insights that would be difficult to detect with unstructured data. Also, I'm a big fan of collaboration. Databases are great for collaboration. They facilitate the sort of collaboration among researchers by allowing multiple users to both access the same data set simultaneously and then foster teamwork and data sharing where you're all contributing, right, to the same environment, the same data resource. They're also great for scalability. right? As your research grows, a database can scale with the amount of information that you're contributing to it without compromising performance. So it's really essential. I don't know if anybody has ever had that experience where you've tried to open an Excel spreadsheet and it just crashes your computer because it's too big, it has too many records, it just can't, your computer can't hold it all, right? So databases are a way to help with that load and allow for you to scale your records over time, right? Also, security. Databases offer robust security features to protect sensitive research data and unauthorized access, ensuring ethical standards and privacy regulations are upheld. Again, we'll talk a little bit more later about access in particular and why you might restrict access. And then finally, relational databases in particular allow researchers to establish connections between different sets of data, making it easier to analyze complex relationships and draw meaningful conclusions. So in essence, databases are invaluable tools that underpin the organization, integrity, analysis, and security of research data, ultimately contributing to more efficient and effective research processes. So different researchers might use different types of databases to do their work. Not all databases are made equal. I'm going to go through just a couple of scenarios to give you an example of what I mean by this. So first and foremost, and we see a bunch of different kinds of database models here on the right, but I'm going to go through these a little in more detail one by one. So for example, a historical researcher, right? A historian is compiling a database of primary sources, primary source documents from the 18th century, including letters and diaries and official records. And the historian uses a flat database to store these documents in a single table with columns representing attributes such as the document's type, author, date, and location. This is a great place to start when you're starting your resource. A flat database is perfect for just getting your data organized and standardized. And this allows for easy retrieval and simple searches based on these various criteria. Let's think about sociology research example. So say a sociologist is studying the effects of urbanization on a community community relationships. The researcher creates a relational database to store survey data, interviews, and demographic information. Different tables are used to store survey responses, interview transcripts, and demographic details with relationships established between all these tables to analyze the correlations and patterns in the data. So, for example, this is a entity diagram here that sort of shows you how a relational model might work, where you would pull from different tables into a single table, right? Where these things are controlled by outside tables. So essentially, you'd have, something that an independent or a key for managing one content type and then a different key for managing a different content type. We'll look at more close examples of this later on in the workshop. So then let's think about a digital art archives example. A digital artist is curating an archive of multimedia art projects, including images and videos and interactive installations. So this artist might use a NoSQL database or a NoSQL database to store these diverse types of data, which allows for flexibility, really for flexible data models and efficient storage of unstructured data. So this database supports the artist's needs to organize and retrieve various media formats based on the project's themes or dates and collaborations or collaborators. And what you can see here in this example on the right is that, you may have tables for all different parts of the data, and then you may form connections between them, and some may go back and forth, right? Some may contribute equally to each table. Others may be just one way. So a NoSQL database has that sort of increased flexibility as you build it out. Then there's, this is a linguistic research example. So for specifically thinking about graph databases. So say a linguist is studying the relationship between different dialects and languages. The researcher uses a graph database to map connections between languages, including phonetic similarities, shared vocabulary, and historical influences. The graph database enables the linguist to visualize and analyze these complex relationships, revealing patterns and connections that might not be apparent in a traditional relational database. And you can, again, learn more about graph databases in more detail in part 2 of this workshop with my colleague, Brian Horn, which will be held on the 10th of this month. And again, from at the same time slot, 10 to 12. And this is an example of a graph database from his work. And so you might want to, again, he'll go into more details if you attend his workshop. And then finally here, let's talk about a SQL database example that relates to social sciences or public health. So maybe a public health researcher's tracking the spread of infectious diseases in different regions. The researcher uses a SQL database to store and analyze data on infection rates, vaccine records, and healthcare access. And using SQL queries, the researcher can filter data, identifying trends, and generate reports to inform public health policies and interventions. So these scenarios illustrate the versatility and importance of different types of databases in supporting diverse research projects across various disciplines. So let's get into some central concepts here, because I think that will help ground us a bit more. We know that the creation of data involves modeling, right? We take discrete data points and we label or categorize them, and then we organize them so that they can begin to, so that we can begin to understand these discrete data points in relationship to one another, right? And hopefully see things like connections or trends or outliers that become meaningful to our research. So this is a really fantastic just visualization of some of these basics that a colleague, Miriam Posner from DH&IS, has put together, and I use it in my Introduction to Digital Humanities courses when I teach them, because I think it just breaks things down very, very clearly in terms of basic vocabulary. What's known as the content model can also be called a schema, content schema. And basically, these header columns, right, or headers of the columns, that's what's known as the content model. So all of those things together, all of those headers together are known as the content model. Those are the things that you're collecting or organizing your data around, right? The specific entities or content types that you're collecting for or organizing around. The whole thing together is known as a table, right? So when we talk about various different tables and their relationship to one another, right, that is in regards to the whole set of records, right? And records are the rows, the individual rows that fill in the information for each one of these content types. So when we talk about a flat database, it's a type of database that stores data in a single table, similar to a spreadsheet. And this table consists of, again, rows and columns where each row represents a record and each column represents a field or attribute of the record. There's always an act of interpretation when we create our data models. We're deciding what's important for our research and what information is not, right? These decisions shape the trajectory of the project and should anticipate future uses of the data. So it's really important to follow some best practices here. When you go about making your data model for flat databases or spreadsheets, you should really think about the following. Identifying information that can be described unambiguously in your sources. Creating a set of labeled categories that are clear and distinct, that often maybe rely on standards. And we're going to talk about standards in a bit. Deciding which categories will be specified numerically, or by true-false values, or by descriptive terms. Those, or what we know as strings, often called string data, right? Because these, the way that data is created will then dictate how it can be used. It should assess the difficulty, or you should assess the difficulty of keeping your entries consistent, right? How difficult is it going to be to normalize your data, to bring everything into sort of a consistent alignment? Sometimes that it really depends on where your data came from, how it was generated. If you're the one creating the data, right, then there's certain ways that you can set up your surveys or your the way that you're generating your data, right, the forms, to give you a more consistent result. That also, though, can limit nuance, and we'll talk a little bit about, you know, making those decisions or those sort of value assessments. You do want to try to standardize the format for each data type, particularly when it comes to things like dates and places, but also names. Limit the vocabulary for description, except in the comments, right? That's a place where you do want to let your sort of text do the work. But when we can, it makes sense to limit vocabulary or to stay consistent in our vocabulary throughout our data. Again, in order to allow for it to be usable in different circumstances. And then really read the categories you have established to see what the data model will take from the original sources. And think about if there's other things in those original sources that, or silences that maybe your original sources don't cover that you think is actually really important as you put your data together. Maybe you need to rely on additional sources or find additional sources to provide you with other types of information that are relevant to the body of work that you're trying to put together. And then check for assumptions about categories that may embody bias. You know, we always have to be reflective in our processes, and check your data model for completeness and accuracy. So obviously spreadsheets are powerful instruments for intellectual work, especially in a structured data format. What would be an example of bias in a database? That's a great question. So we'll talk a little bit more about ethics later on, but when you're, there's a great article that I assign in when I teach DH by Michel Roth-Trouillot. And he talks about the silences in the data. And when I'm talking about silences in the data or bias in data, often it's what you choose to collect is a ontological choice, right? It reflects your worldview, what you think is important. And so when you're picking categories, and we'll get, again, I have a slide in a little bit that'll get into more detail, but when you're picking your categories, your content types, you may be choosing to collect certain kinds of information and neglecting to collect other kinds of information. Right? We can't capture the whole world, so we have to make decisions around what we can capture. And by doing so, we place a particular emphasis on what we deem as important. So it's more about your positionality and how you're communicating that, right? Bias is sort of inherent in all data, but it's being aware of why you're making the choices that you're making. That's what I think can help combat bias, because it adds transparency. But great question. So AI machine learning tools are certainly making flat database building easier. But for data to function effectively, certain conditions must be met, which can pose practical, intellectual, and ethical dilemmas. So the schema or structure we give our data, as you were just sort of, as we were just talking about, will impact what we can do with the data. And, really be it how we call information up from searches or how we visualize it in charts. First and foremost, data will need to be uniform and standardized so that it is machine readable. So this sounds simple enough, but for example, some dates might only be specific to the year, some to the month and day, and others maybe to an hour or minute, right? Depending on the kind of data that we're talking about. Methods for recording time and dates are often local or historical. And the start points for example, the calendar in biblical, Islamic, and Mayan systems are all different. So how are these dating systems accommodated? Simply subsumed into a modern Western calendar? Well, maybe not. Standardization can erase specificity and cultural identity, so immediately issues arise in making data uniform. There are other practical things too to consider. What if you're studying a group of artists and their work, and you have some works that are exactly dated and other works with no date, but a set of pictures that maybe show an artist working on a particular piece over several months? How do you enter that into a spreadsheet, right? Just the practicality of like, oh, I have pictures that show, this particular artist working on a work during these months. The work itself isn't exactly dated. Do you pick a single date closer to the end of production, or one toward when the artist started the picture, or you think the artist started at the picture, or do you use a time span? An authority or standard can help us decide which format to pick and give us a reason for our selection. And also acknowledge that we're not representing the information in other ways, right? We're choosing to represent it a particular way. We're being transparent about that decision. So this contextualizes our decisions and the information, which I think is really important. Again, to sort of address bias and think about bias critically. So that's why standards help guide us in creating clean data. They're an authority that can help give us a guide rule to follow. The problem can be, however, that standards are like toothbrushes. Everybody wants one, but nobody wants to use anybody else's. So choosing a standard can be hard because each data set has unique features, right? We're all very special snowflakes. We all have our reasons for wanting to approach our data in our way. That's what makes original research, right? Sometimes we therefore have to make up our own set of rules. If we do, what becomes most important is that we stay consistent to the rules that we set for ourselves throughout the project. So everyone has to sort of be in agreement about then what is our new content standard or standardizing rule for our data, and we have to all commit to carrying that forward together. For instance, say you had to complete this short survey on the left here about pets and animals. So let's look at these example results that you can see here on the right to show us a little bit about data capture methods and data cleaning. I'm going to open this doc over here. And what might you originally notice about this data? What stands out to you?
There are discrepancies in some of the answers. Some people say no, they don't have a pet, but they also do mention that they do have a pet.
Right, right. Well, and fairly, I said, or write your favorite animal, right? So if they said no, they don't have a pet, maybe their favorite animal is dogs. But we are also seeing, right, that great point, Alex, right? It's all, or in Jeff, it's all over the place. The text entries are not uniform. So when someone is being asked an open-ended question, they're not thinking about your standards. They're just responding, right? And so for them, we get a bunny is a super cute one. We get parentheticals. We get lists. We get little stories. We have all different kinds. We get numbers, right? People who put in they have 5 cats. So we get all kinds of different answers. Now, what I did in the first question here is I only gave them the ability to choose yes or no. And so if I needed to quickly make a chart with this, right, I can find out the percentages really quickly on that, right? I can say, oh, 44% of this group do not own a pet, but 55 plus do. That's really useful in terms of being able to visualize my data. But what's my project, right? Maybe my project is to understand the community feelings around animals. And so the nuance of actually all of this messy data is more of what I'm trying to get after. But then what would I have to do to be able to visualize something like this? Because if I try to visualize it right now, this is not really useful at all. So what would need to be done to create a more effective set of data? I'd have to make some decisions around how to standardize, right? How to normalize the data. I could change the question that's asked. I could give them a pick list. That might be one, right? That they'd have to pick. I could choose the way that all of the data is represented, right? So that they'd have to choose from cat, dog, guinea pig, squirrel, dolphin. And all of that could be standardized on my side. I could split it into multiple questions, separate types of pets from the number of pets. Absolutely. Break the question down further. I can also, in the aftermath, I can look at this data and I can say, I want to make sure that all my data is singular and uncapitalized. So I can go through and I can use some kind of data cleaning tool like Open Refine, perhaps, to do data transformations and bring these things into alignment. So I can change cats to cat. I could change 2 dogs to dog and go through and standardize my data to make sure that all of these things read the exact same way or follow the exact same standard. And when I do that, then I can visualize this quite quickly, right? Or have my database run a query and answer how many people prefer dogs, and it can give me a number, right? So when we talk about database normalization, it's the process of organizing the data, particularly in a relational database, but really any kind of data to reduce redundancy and improve data quality. So these are the things you're going to want to assess when you're looking at other data sets and when you're putting together your own database. So when we are cleaning our data, these are just a few questions to ask ourselves as we go. Are all the data formatted in the same way? Are all the quantities specified explicitly? Is spelling consistent? Do fields contain unambiguously unique information, or do they need to be split? Is the vocabulary for qualitative judgments consistent? Is the information missing or incomplete in many fields? Is there repetition of information? And will the information be able to be filtered and sorted accurately, right? Can I do the kinds of transformations or queries that I want to do on this data? And I think I want to pause here because I want to point out one important concept that was in that list. And it's a really important concept to understand and implement in relation to data organization. And that's the idea of, or the concept of the unique ID. This will be an alphanumeric ID that is exclusive to an individual entity, like a person or publication. So I want to read you a scenario from Drucker's book because I think it's a perfect example to give. So imagine you are inventorying the manuscripts, correspondence, and memorabilia linked to publications by an author. The columns will be labeled as information fields, such as standard biographical information about publication date, publisher, length, edition, and so on. The author whose archive this is will remain the same, but the authors of the correspondence should be given their own unique ID. In the inventory, each item about which information is being entered should also have a unique ID. This will allow the material to be identified efficiently and unambiguously. For instance, if there are 3 manuscripts for one book and 4 letters from one person in the same year, giving each a unique document ID eliminates confusion. The decision about how granular this should be depends on the project. For instance, if there are 3 manuscripts of the same book, each has a unique identifier and also some distinctive information about its place or date of production. But what about miscellaneous things stuck into the manuscripts at random? A letter from a friend, a holiday photograph, a note relevant to travel arrangements, for instance. Should these have unique IDs? Are they separate documents? Or do they, quote unquote, belong to the larger manuscript? For whom is this information useful and how will it be used? The ephemeral documents are not, strictly speaking, part of the manuscripts. They may contain information that needs to be structured differently. A manuscript generally does not have a recipient or a sender, and correspondence does, for instance. So representing this object in the same database or data model as the manuscript raises questions. If a later process sorts all items in the spreadsheet by date, the additional items will need counting. If the postcard is from a friend, it will have a different author. The purpose of structured data is to make research and analysis possible without confusion. So consider these types of things when putting information into a spreadsheet, right? We have to pause and really reflect on, before we even get started, what kind of information we have and what are all the possibilities, the various iterations that may come about as we're dealing with this information. And do we have a structure for that? Can we accommodate it in our structure, right? And unique IDs can help a lot with that. So please always make sure that you are generating unique IDs for your data. They play a crucial role in database construction for a number of reasons, including things like uniqueness, right? Erasures that, or I should say, ensures that every record in a database is distinctly identifiable, preventing duplication and ambiguity. Obviously, that's in the name. But also things like indexing, right? It facilitates efficient indexing, which can speed up search queries and improve overall database performance. It also allows for the creation of clear and reliable relationships between tables, right? Which is fundamental for relational databases. Helps maintain data integrity by ensuring that each entry is unique and cannot be confused with another entry. When it comes to scaling a project, right? The unique ID ensures that even with millions of entries, each record remains distinct and traceable. And for security, right, it helps to ensure secure access and updates as operations can be restricted to specific records identified by their unique IDs, right? You can give access based on these unique identifiers. And also it's critical for maintaining referential integrity in a database, ensuring that foreign keys can reliably point to corresponding primary key entries. So again, when you have tables pointing toward one another, those unique identifiers are what is going to ensure that that pointing or that connection between those tables is happening in a reliable way. So flat databases are typically simple and do not have the capacity to establish relationships between different tables, which makes them straightforward but less efficient for complex data management tasks compared to relational databases. So as data becomes more complex and relationships among elements of the data more elaborate, neither flat, sort of spreadsheet-based databases or hierarchical structures like XML or JSON are efficient for managing or processing. So this is because specifying relations among elements of data can be a benefit for defining, storing, and processing data. And the shift from flat databases to relational ones is conceptual as well as technical. Understanding when and why such a shift should take place, as well as how to implement it, is crucial in making a relational database. So again, I may sound like a broken record here, but you make these switches to address things like data complexity, right? A relational database can handle multiple related tables, and so it can handle more complex types of information. It helps with, again, redundancies and integrity of the data, right? Minimizing inconsistencies. It's really essential for complex queries and data manipulation through something like SQL. And we're going to look at SQL in just a little bit here. But when you're trying to do really sophisticated data filtering and generating of reports, right? Getting really precise in the kinds of queries that you're trying to do. Database is the really only way that you can do that extremely effectively. And again, helps with scale, helps with those relationships, helps with collaboration because you can have multiple users in the environment, and helps with security, again, to be able to control what's sensitive information, what should people see and not see, because you have it in individualized tables. You can dictate who has access to what, and that can be called up depending on a user's status. So very simply, a relational database is composed of multiple tables that separate different types of information to make it more efficient to manage and easier to control. This is true of any scale, but becomes more pressing in larger projects. As the scale and complexity of databases increase, so do the challenges related to cross-functional exchanges and the right of communities to determine their data profiles in use, and concerns about privacy and ownership of that data come to the foreground. And again, we'll talk about this more a little later on, but separating data tables out can really help give you that level of control that, depending on how you user access, right, you can really be thoughtful in how you grant access to what kind of information. But here's an example. I think this is just really straightforward of how a relational database operates, right? You have these unique IDs that get pulled into a table. So for all student courses, we have the student ID, so the student itself, the student themselves, and the course that they're taking. And these things are all controlled by either a student table or a course table. And so then that ID is what gets pulled in here. So they're referencing, when you say student 1, I'm referencing Sam. And it's student 2, it's obviously Mary. And Mary is taking, she's taking course 3 and 4. Well, course 3 is on MongoDB and course 4 is on Java. So that's how relational databases work, right? They use other tables as sort of lookup tables, right, to find that information and bring that in relationship. So the relationship between those tables is used in terms of a structure. The basic components of a relational database are somewhat more complicated than those of a spreadsheet, but they're conceptually similar. A table structured, is to store information, and each row is still a record. A form is a screen designed for entering information into the database. It is the front end of the tables, essentially. Multiple forms can be built on top of the same table, set of tables. So you may have the same sort of back end, but you may have different forms that you use to comb that back end or to pull information from that back end, or to add to that back end, right? It could go both ways. A database of biographical information might have a front end, which readers put comments or rankings and add keywords or tags to. But another form might be reserved for researchers who are establishing the biographical details of the same authors in a consistent manner and linking them to various authoritative bibliographical databases and what are known as name authority files that help disambiguate one author from another. Reports are the output of queries to the database. So a user might ask what an author published in a particular year or with a particular publisher. If a user is going to be able to query across a span of years, then the database has to be set up to accommodate this, or a user will have to query each year individually. A database management system allows the database to be used for generating queries and reports, and then also for visualizations and displays, export functions, and other operations. So including things like being accessed live on the web, right? Doing live queries. Most common database language is SQL, which stands for Structured Query Language. And we'll get into that right after we discuss some basics around database design. So let's talk about some database design. The basic steps for designing a database are pure simple, right? So designing the content model, so defining the information in the database and its organization, define the fields for the data entry, and design the relationships between them. Then you would build a form-based entry for putting data into the database. This might be organized very differently from the database in order to make it more useful or coherent, depending on your users. And you don't always necessarily have to have a form. There are different, you don't always have to build the form. there are content management systems that do this for you, and we'll talk about this in a minute. And then finally, manipulate and use the data through searches, queries, reports, and other methods, including visualization and analysis. So what is most time-consuming and the real intellectual challenge here is around building a content model. You need to understand a map and map out how all your information is going to fit together. These are content model squiggles by myself and my colleague Ryan Horn just recently for another project that we were working on. You really want to think through how this information fits together, and it can be a messy process. For example, the power of a relational database resides in the ability to control information carefully for consistency, but also for analysis across fine-grained features of the data. Attention to the design phase, to what pieces of information are dependent on which should be carefully tested against scenarios for future query and use. This can be done on paper without ever building anything digital, and in fact should be, right? Do the messy squiggles. They're necessary. And we often call these kinds of drawings, whether it's with as neat as this with a particular program or squiggly like this, we call these entity relationship diagrams or ERDs for short. Once the database construction is underway, tools within the applications such as visualization of tables and relations will be extremely helpful to see the shape of the conceptual model and the argument it contains. Tools for building databases with visual means exist as well. So for those whose logical faculties work better in graphical form, you can do it that way too. That would include me. I find this much easier to think through and manage than working in a spreadsheet all the time. So sometimes depending on how you like to build your databases, right, you can think about what format is most useful to you. These are content models that are also essential for crosswalking. And mapping between models. You have to sort of do this work in order to then also think about how do you share your work and how does other work get pulled into your content, right? If you want to expand your content over time, you want to work with other kinds of data sources. You also have to think about how they're structured and how those structures are going to relate to your structure. If you've ever tried combining your data set with someone else's, you've experienced this this challenge. If you don't use the same headings, for example, or your tables aren't organized the same way, it takes effort to bring one set of data in alignment with the other. So I find that real world examples often are the best way to bring concepts to life. So I want to share from a project I've been working on with the Fowler Museum. Vital Matters Art, Devotion, and Practice is a digital initiative that represents different perspectives on devotional works at the Fowler Museum, objects that arouse devotion, awe, and serenity, mediate relationships between human and spiritual realms, and are often of vital importance to cultural heritage and individuals and communities. This project brings together academic knowledge produced in museums and universities with knowledge embedded in the practice of spiritual-based leaders, artists, and community organizers. Together, their insights shed light not only on the materiality of belief, but also on the vital matters of today, such as public health, the environment, and education. So for this first iteration of the project, it focused on 5 main objects, and there were many, many interviews that were videoed and held with a number of participants on a variety of topics related to a specific object. So this is how we ended up organizing ourselves for our initial workflow. I'm going to just share some of our working documents so you can get a sense of things. And these are sort of flat database structures that were edited over time, depending on what we needed to track. We were sort of building the plane as we were flying it, so we wanted to be flexible with the thought that eventually, or with the knowledge that eventually we would be moving into a more sort of formed content model. But we wanted to make sure that we were ready for that. We were also working with people of all different technical backgrounds, right? And various kinds of expertise. So when you're doing that kind of work, right, you also want to be sensitive to different needs, right? Different participant needs. So here, initially, we just tracked our speakers, but then we realized, oh, I edited some things, a colleague of mine, Jean, edited some things. Eventually, we had another consultant, Decker, that edited some things, right? So we needed to track our editors. For now, we just use first names because we're not really part of the project. It was more for our workflow. But maybe down the line, you'd want to track all the people involved in the project, not just the speakers, right? But like everyone who ever participated in the project. So then you might want first name, last name, and you might want to have a whole people table. I'm going to show you examples of this in a minute. Speaker title and affiliation, right? We tried to be just consistent in this format, but you may want to break this down even further, right? So that, again, you think of these things as discrete data rather than sort of a combined, okay, that's their title and their affiliation all in one form. We had things like a temporary title for the videos that we were working on and a final title, right? We had thematic tags. Again, we tried to be consistent with these as we went along. This could have been a pick list, right? We could have set a pick list and then added to a pick list, and those things be generated from just a simple pick list. In this case, we know this is, can be exported as a CSV file, so very easy to separate those out as needed and create a list from them. But again, being consistent as possible, right? And how we referred to things. We have our links, right, that we pulled in for API purposes and to our videos and our assets, both to the original files and where they're stored, as well as where they're hosted in the cloud. And then here's a yes or no, right? We wanted to know, does this particular video annotate the object directly? Depending on the content, we chose for it to or not to. We also chose where, if it did, right? And this was all kept in one column. Probably best practice to separate that out, right? But depending on the content model, we weren't sure how all of this was going to fit together. For now, for working, that keeping that information together made sense. And then edit notes, right? Ways that we talk to one another in our document. This is free form, never going to be data, just a way for us to take notes and share notes with one another. You also see here there's an artwork metadata, that tracks which particular piece, right? And the information of that particular piece these videos are in connection with. I'll close down our pet data here. I'll show you just another example. Right, so we had, for this one, we had, a number of different participants, right? And this is organized by the objects, right? So you'll see this is TOD stands for Tree of Death. That is a work by Veronica Castillo. This Jane refers to this Jane tapestry that this work was these conversations were in regards to. So we were organizing around the objects themselves, right? And again, here you can see our data is organized, but maybe not normalized for a relational database. So what would that look like? Well, when we started to do that, we asked ourselves what were the central parts of our project and how did we want to build that out in a website and what components needed to relate to one another. So obviously the people doing the work became essential, or the participants that were being interviewed became essential. So we separated out their first name, their last name. You can see everything got a consistent content name, right? Content type name. And then we have a unique identifier for every single person, P001, and so on down the line. We left room for role, but for now we separated out title and role being like what was their role in the project. So they would be experts or participants or something like that, right? We'd have to define what that language is. And if we chose to, in this case, we were only including the experts, but if we, again, expanded this to also be a database for everyone who ever worked on the project, right? Then you'd want to say, okay, someone was an editor or they were, a director or that sort of thing. In this case, we separated out the title, the department, and the institution, and some had multiples, right? So if they had multiples, well, then guess what? You repeat the fields, title 2, department 2, institution 2, up to 3, right? We have people who had up to 3 in their titles. So you have to think about, again, those content types very specifically so that your file naming structures and your content types, all of those things become consistent. You have the files, right? You have, they might be located in different places. You have descriptions, right? Bios, those can be just put in as text. But then you have things like related media references. So this is pointing toward the media table. So all of these are media ID, unique identifier tags. And this is saying this particular person is associated with these media references. And the artwork, right? They were also associated with individual artworks, right? They're talking about their interviews were in regards to particular artwork. Well, then those are part of the artwork table, right? And so all those unique identifiers are pointing toward that particular artwork that they spoke to. And so you start to see the connection between the tables, but the content types are different for each table because you're tracking different things in each table. So here, these are the media files. They have their own titles. They have they're a media type. Sometimes they're images, sometimes they're video, right? You want to be as standard as you possibly can with those. Now, when we add description here is for accessibility purposes, for WCAG standards. What is the alt text that you want in your, you want connected to these particular images or videos, right? That's a really important thing in terms of accessibility. So that goes into what we call description here. You have the source URL for the actual video or image, related media references, and also themes. So each one of these videos, as you saw from our working doc, right, they had different themes that were associated with them. And what if you wanted to search your videos by a particular theme? Well, you'd have to have them tagged, right? And so we have a theme table here that has a unique identifier for all the different themes, right? Those are all standardized. So no matter what, you're always using the same number to represent activism. And then those are associated with different media, right? So this is every single video that references activism so that you can pull that up, right? That can be easily pulled up through your database. And it also shows what different artworks that theme is associated with. So what that means then for the themes that you set, for instance, if I tried to combine, if I decided, okay, we've done all this work, but you know what? I actually think that like art market and artistic practice, as well as contemporary art, could all be one category, and I could call it, you know, just arts. I'm being obviously very general here. But if you were to do that, what would that mean for this table and my other tables? What would happen there? Would that be an easy change to make? Why or why not? So changing or combining fields, it's one thing to add, right? If we add, we just tack on another unique ID to the bottom of this, and we add a new one, and we go through and we label it. That's not that bad. But if we were to change, well, one-for-one change is fine. But if we were to combine or to substitute a new term to cover multiple terms, that would mean that we would have to rethink or go back and redo all of these references that point to one another, right? Because all of a sudden, that category isn't pointing in the same way anymore. So this is why it's really important to take the time at the beginning to think through your content model, and how you're structuring your project, because those things can be harder to change down the line. So it would mean that all of that would have to change. And so then you would have to go into these and change them here, and anywhere else across the database. There are transformations that can allow us to do that, but we have to think really carefully, because it affects so many different fields all at once. So I hope that that was a helpful example of how you can move from a flat database to a relational database, and why you might do that. I also, I should just mention, right, when you're in a flat database, right, you can do things like filtering. There's, for example, you can add a filter, and I could filter by particular person. So you can do some really, now I can see only Lena's records right here. So there's filters that we can apply, and we can have multiple filters running on different kinds of things to filter down our information. So we can do sort of queries or data searches that way, and then visualize based on those informations within a flat database. And that's very useful. But it just we're able to do so much more and get so much more granular and intricate when we have relational databases that we're working with. Great question. So we have a question here that is there ever a time where simplifying or generalizing themes is better than separating them in more specific themes? Absolutely. I think when you're using more general themes, right, you're going to have less themes, and so you have bigger buckets essentially, and it's going to allow for you to more easily sort that data. When you separate them into more specific themes, right, you then have to be really clear about why something is getting sorted into a particular category. And so you and your team, I think what's helpful here, and what we had done too, I'm not showing you that work here, but we had sort of defined for ourselves what do we mean by agriculture as opposed to our tagged land, right? That those things are not the same. And here's why, right? Like that we've had our own team understanding of how things got labeled. But for instance, rather than agriculture, you could just put everything under land. And certainly that would, you could take these tags and just say, okay, anything with agriculture, all of that gets moved into land. That's fine. And that's an easy enough transformation to combine in that way. It's more difficult when you're combining very different types of themes, or breaking them down into such granularity that your searches don't give you a lot of meaning, right? If you have only one or two things in a category, then you might think, is that category worth it? Is it doing what I need it to do? Maybe it is. Maybe it's identifying outliers. But it just becomes important to understand the why, right? A great question. Oh, so if one wanted to make significant architectural changes to a schema after the database was designed and deployed, wouldn't it be easier and safer to rebuild the database from scratch with the schema modifications you made? In some cases, Dave, yes. It really depends. Obviously, how big, time scale, all of that has to be considered. But in some cases, yes, that might even be easier. Particularly if you have scripts that are helping you, right? If you're using Python scripts or other kinds of scripts to help you organize your data, that could be, you just rerun it, essentially. So great point. So if you don't want to roll your own content model, that's fine. You don't have to. Not everybody has to build a database from scratch. In fact, I don't think everyone should. Because there's great CMS options out there. And I want to talk about two different kinds of CMSs here, just briefly. This is really more aimed at cultural heritage, for cultural heritage management, but I think it can be applicable to others as well. So content management systems and collection management systems are both common in the management of cultural heritage materials and objects. And collections management is just what it sounds like. It's a way to describe and manage collections. The task for collections management includes everything related to tracking objects or artifacts, making records, keeping updates for acquisitions, conservation treatments, loans, and so on. By contrast, a content management system is designed to create and present content in a web environment. Both of these systems have database backends, and common content management systems include Omeka, which was created by humanists, WordPress, and Scalar, also designed for humanities and media work. These will be discussed. I'm going to talk a little bit more about these later. But the point is that in both cases, backend organization of data is managed in a database, and whatever platform or application is used to create a database and manage it, the crucial intellectual issues are expressed in the data model. So the conceptual frameworks of relational databases that differentiates them from flat spreadsheets and hierarchical XML structures is that they consist of linked tables. And so when we're thinking of making use of a content management system, a lot of this is happening through WYSIWYG, or what you see is what you get types of interfaces, that and is doing that sort of relational connection in the back end for you. So you're filling out forms that are asking you, like, what kind of media is this? Well, it's an image. What kind of, like, who is the creator of it? It was created by Francesca. And you're filling in that information, and then that's all being managed and pointing to different, they're on the back end. It may be operating in relational databases. So it's following standards so that you don't have to. You don't have to really think about that, but you have to be aware of what standards are being utilized. So again, here, and I know we're running short on time, and I haven't even gotten to SQL yet. So I'll just say, when it comes to information in these tables that are in the back end, right? There are specific standards that often govern those things, and so you want to be aware. And we're going to talk about that again a little bit more later on, what those specific standards are and how your tables are being linked. Yeah, I think that's, let's get into SQL. That's, I think, the most important thing to know about your relational tables for your databases. But SQL is a standard language for accessing and manipulating databases. I should say SQL. I'm sorry, SQL is the precursor. SQL. SQL is became a standard of the American National Standards Institute, or ANSI, or ANSI, in 1986, and the International Organization of Standardization, ISO, in 1987. Although SQL is an ANSI, an ISO standard, there are different versions of SQL language. However, to be compliant with ANSI standards, they all have to support at least the major commands, such as select, update, delete, insert, where, and we'll learn more about those commands in a second, in a similar manner. So all of these SQL languages do have to do that. And most of the SQL database programs also they have their own proprietary extension in addition to this SQL standard. So just know that what I'm sharing with you today is based off of Web3, W3 schools. So it's going to give you the sort of most popular standards, but depending on what database platform you use, there may be slight differences in the commands and some additional proprietary commands that they have for their particular SQL database systems. Before we sort of demo how to use these commands, let's quickly review the main components of an SQL database. An RDBMS, a long acronym there, but it stands for Relational Database Management System. RDBMS is the basis for SQL and for all modern database systems, such as MS SQL Server, IBM DB2, Oracle, MySQL, and Microsoft Access, just to name a few. The data in RDBMS is stored in database objects called tables. Again, same vocabulary here. A table is a collection of related entries, and it consists of columns and rows. Again, all of this is sort of familiar, I hope, at this point. I am going to bring up an example here for us to take a look at from W3 schools. Be a little more interactive. So, right, we've got a database over here. We've got, these are our various different tables. And we have a readout of how many records are in each one of those tables. So every table is broken up into smaller entities called fields. So I'm going to run this query here. We'll talk about this, the SQL statement. Talk about that more in a minute. But essentially, I've just brought up that table, and I can see all the rows, right? The fields in this particular customer table consist of customer ID, customer name, customer or contact name, address, city, postal code, and country, right? These are what are known as fields in SQL. they're also known as content types, right? That's what I've been referring to as content types. But in SQL, it's fields. A field is a column in a table that's designed to maintain a specific or to maintain specific information about every record in the table. And a record, so known as a row, is each individual entry that exists in a table. So for example, there are 91 records, 91 rows in the customers table. A record, again, is that horizontal entity across. A database most often contains one or more tables. So we see over here, right? My database has several tables. And each table is identified by a name. So in this case, we're in the customers table, right? But there's also the orders table. Look at the orders table, right? And if you noticed here, right, my SQL statement shifted depending on what table I selected. So we're going to talk about how you actually construct these SQL statements now. So most of the actions you need to perform on a database are done with SQL statements. SQL statements consist of keywords that are easy to understand. So select extracts data, update updates data, delete, obviously we'll delete data from a database. Insert into is how you add new data. You can create a database, right? You can alter the database. You can create tables, alter tables, right? Those tables themselves. So you have these commands that allow you to do those things. And so we're going to look at some examples together just to demonstrate generally how this works. So you'll see up here, select asterisks from and customers. This allows me to select all records from the customers table. And if I were to, again, edit this and say employees and ask it to run, it pulls up the employees table, right? All 10 rows of the employees table. So the SQL keywords are not case sensitive. You'll notice I didn't capitalize employees. And if I typed in, select instead of like lowercase instead of uppercase, that would still have the same effect. You'll often see the commands done in all caps because it helps to differentiate them. It's just easier on the eye. So let's say I want to select multiple things, right? What I can do in this SQL or SQL syntax, right, is column 1 and column 2 are the field names of the table that I want to select from. And then the table name, right, is where I want to pull my data from. So if I were to say, I'm just going to pull over this so that we can fill it in. So if I want to say select last name and first name from see, we're in the employees table, right? oops. And the you'll see that some database systems require a semicolon at the end of your SQL statement. The semicolon is just the standard way to separate each SQL statement in a database that allows more than one SQL statement to be executed in the same call to the server. So again, as you sort of stack these things, oops, let's try that. There we go. Thank you, Dave. So basically, what I'm saying is select from that column and this column, right? Those two names, and then from that particular table. And that's what I get returned. So I'm able to make a certain call for information and pull that particular information out. We can also do what's known as a select distinct call for query. So inside a table, a column often contains many duplicate values, and sometimes you only want to list the different sort of distinct values. So select distinct statements, if used to return or is used to return only like distinct or different values. So if we go to, for instance, back to our customers table, right? Got to add from, right? You have to add where you want to pull from. So when I bring this up, right, I have all these things, but there's some that are duplicates. So say I want to say, just give me the select distinct. City from customers, right? And now I have just the distinct customer names, not their repeats, and their city names. Make sense? So now if we were to want to add data into our database, right, using SQL, you would use the insert into statement. That will add a new record or new set of records into a table. It's possible to write insert into statements in two ways. You can either specify both the column names and the values to be inserted, like this, or if you're adding values for all the columns of the table, you don't need to specify the column names in the SQL query. However, make sure the order of the values is the same order as the columns in the table. So that way those things line up. And just to show you what that looks like, right? If you were to insert into customers, you'd again use the headings here, right? The field names. And then you assign the values, right? So here, what we've done is add this row down here, cardinal for Tom, his address, right? We added all that information in here just by listing the values in order. What you'll notice though is that the customer ID was not something we added. The customer ID is an auto increment field and will be generated automatically when a new record is inserted into the table. So you didn't have to do that when you're doing your identification and adding into. the database. Another thing that you probably would like to be able to do when you're working in a database next to adding a record is updating one. So the update statement is used to modify the existing records in a table. You'll want to note and be careful when updating records in a table that you have to very specifically notice this where condition, or the where clause in the update statement. The where clause specifies which records or which record or records should be updated. And if you omit the where clause, then all the tables, all the records in the table will be updated. So again, the where condition or where clause is really important. So this SQL statement updates the first customer here, right? Customer one, I'm saying, okay, where customer ID 1, this row, well, what do we want to do? We want to set it as the contact name. We want to change it to Alfred Schmidt, right? Right now it says Maria Anders. If we set contact name, it's going to change that contact name for us. And we also, so we're doing 2 transformations at once here, can also change the city from Berlin to Frankfurt, right? So you can see just from that simple statement, we're able to do the change. I see a question. What is the SQL server that we can use for free for building our database? Great question. I have a whole list of those that I'm coming to soon. So as soon as I get through these practicing statements, we'll talk about different database options. So you can use, you can also use update to change multiple records. It is the where clause that determines how many records will be updated. This SQL statement that you see here will update the contact name to 1 for all the records where the country is Mexico. So you'll see, right, these things got changed. I will again caution you to be careful when updating records. If you omit the where clause, all the records will be updated. And then delete is sort of the final thing that I think you'd probably want to do, no matter what. So the delete statement is used to delete existing records on a table. And again, be careful when deleting records on a table. Notice the where clause in the delete statement. Those where clauses are really, really important. If you don't specify or omit the where clause, all records in the table will be deleted. So you want to avoid that. It is possible to delete all rows in a table without deleting the table itself. And this means that the table structure and attributes and indexes will be intact. So you can just sort of wipe the table out and add information back in. And Dave, to your comment earlier, right? Like if you just wanted to start from scratch, maybe you need to add in something to your table and then add data back in, you can do it that way. I should say the SQL statement that deletes all, right, would be delete from table name. And then to delete the table completely, you use drop table. So for example, drop table customers, and that's going to just get rid of that whole table completely. And then just to, again, show you what deleting information looks like rather than deleting full tables and things. If you wanted to delete, for example, from customers, this name, right? You can see that the customer ID went away. That particular person is no longer in the table, right? Because we just said delete from this contact, right? So it knew to delete that row. So that's how you would make that change. And these queries obviously can be stacked and fine-tuned and for really precision results. Here's an example here of that. And I do encourage you to dig in more on W3 Schools to learn more SQL and sort of all the different kinds of commands that you can do, all the different transformations that can happen through SQL. I see another question. When we delete all the data after ignoring the where condition by mistake, can I revert to a previous step? That's a good question. It depends on the database that you're using and where you're operating within that database and what interface you're using. Usually, yes, there is always a sort of go back. So you're not totally lost. But again, it depends on the particular platform. But yes, and again, this is why also I would say good database practice is that you always have a copy or backup of your database. So there's actually a command to back up your data. And so if you're ever doing sort of deletion kind of transformations, you'll want to make sure that you always have a backup of your database so that you can revert if need be. A great question. Okay, so picking tools. As we're winding down here, let's talk about why you might pick a certain kind of database. So when selecting a database platform for research, it's essential to consider the nature of your data, the complexity of queries, scalability requirements, and the specific goals of your research. Below is an overview of several prominent database platforms, or I should say here on the screen, that and some reasons of why you might choose one over the other. So for RDBMs, SQLite is really best for beginners. It's lightweight, it's easy to set up, there's no server required. It's great for learning SQL and database design, often used in small applications and mobile development. MySQL is an open source RDBMS, known for its reliability and ease of use. It's suitable for structured data and supports complex queries. It's ideal for projects requiring ACID compliance and multiple user support. It's probably the most popular open source of all the RDBMSs. It's widely used in industry for web applications and business systems. It's great for learning how databases work in real world applications. And it offers free and community supported versions. So for those who are asking me what a good free version is, I would start with MySQL. PostgreSQL. It's another open source that offers advanced features like support for custom datum types and full text search. It's favored for research needing complex transactions and data integrity. It's best for SQL, for more advanced SQL learning. More feature rich than MySQL. It supports advanced queries and data types. It's used in enterprise applications and data science projects quite a bit. And it's good for learning performance optimization and complex queries. And then Oracle database is another one. It's a commercial RDBMS, renowned for its scalability, robust security features, and comprehensive support, suitable for large-scale research projects with substantial data volumes and the need for high availability. I would also mention here maybe Microsoft SQL Server Express, which is best for Windows users. There's a free version of Microsoft SQL Server. It's good for learning SQL for Windows-based environments, and it's useful if you plan to work with enterprise applications later. No SQL databases. MongoDB, really, really popular. It's a document-oriented NoSQL database that stores data in JSON-like formats. It's ideal for handling unstructured or semi-structured data and allows for flexible schema design, making it suitable for research research that involves like very diverse data types. It's best for document-based NoSQL learning. And yeah, it's great for learning NoSQL concepts and flexible schemas. It's often used in web development and big data projects. Then there's Apache Cassandra. It's a column family NoSQL database designed for handling large amounts of data across distribution systems. Offers high availability and scalability, making it appropriate for research projects that require real-time data processing and analysis. So again, if you're looking for something to be processing in the field, that may make the difference here for you. Graph databases. So you're going to be learning a lot about these with my colleague Ryan Horn. If you join part 2 of this workshop next week, he'll be talking about Neo4j. It's a graph database that excels in managing and querying connected data. And it's particularly useful for research involving complex relationships, such as social network analysis or biological pathways. It's great for learning how to model and query relationships and data. Again, it's used in social networks and fraud detection and AI applications. It's a really great, I think graph databases are really on the rise. We're seeing more and more use of them. So please check out that workshop next week with my colleague. And there's a couple other databases here that I think, depending again on your research needs, may be useful. So in-memory databases like Redis, or time-sensitive databases like Timescale DP, and then something like search engines, right? Elasticsearch. These are, depending on the specific needs of the project, you may select a database like one of these. For research and digital humanities projects, I just want to take a second here to talk about some content management systems that come with built-in databases or support database integration. Omeka is fantastic. It's best used for digital exhibits, archives, and sort of collections-based projects. It uses MySQL. It's designed for scholars and libraries. It has metadata support sort of built in, so it uses Dublin Core and mods built into the platform already, so you don't have to think about those standards, right? They're there, they're already being used. It's easy for non-technical users and has plugins for geospatial mapping and text analysis and timelines. So it's been around for a long time now, and it's a great community platform. There's a lot of different plugins that allow you to do a lot of different things with it. Drupal's been around for ages. I think it's sort of on its way out, but it still is one of the better platforms for just robust, in terms of like, you've got a robust project, Drupal can probably handle it. It's supported by MySQL, PostgreSQL, and SQLite. It's really best, again, for complex, customizable research projects. Things, if you're looking for, it's got a really powerful taxonomy system. It's good for large data sets with complex relationships. And it does have strong community support from DH. When it comes to WordPress, it uses a MySQL database. And I know it's a blogging platform, but honestly, it's still very, very popular. And it's great for whether you're doing storytelling or structured narratives or just putting together a website. That database backend is powerful. It's user-friendly. It's got a lot of different plugins that you can pull from, and it's scalable for different research needs. So again, I think WordPress is one of the better standards. Scalar, which came out of USC, is fantastic for nonlinear storytelling and interactive media publications. It uses MySQL through WordPress framework, actually. And again, it integrates with multimedia and annotation tools, which is great for DH work. It's good for experimenting with narrative and thinking about narrative in different ways. And then I also want to mention Merkutu. Merkutu it uses MySQL. It's really designed for Indigenous knowledge management and ethical archiving. And so when we think about digital repatriation and community-based projects, Merkutu is just leading the pack there. And they've really, really thought about different user bases and access to different files depending on those user bases. So again, we'll talk about sort of some ethics in a minute here, but I think that that's a powerful tool that has that built in. Again, so you can rely on the content management system for those things rather than have to build it all from scratch yourself. Research space and heuristic are another set of CMSs here that are great for like research space supports CDOC CRM for cultural heritage research. Hurist is great for research teams needing structured relational data. And it allows scholars to create custom data models. So again, depending on what you're doing, consider starting with a content management system. It might fit your needs and then you don't have to start from scratch. As you pick a platform, you will want to consider what standards that platform may have already built in. If not, what standards or linked data you will want to make use of for your project. Again, I won't go into too much detail about this really complex graphic, but the point here is that there are standards for all types of data, and there are those that are domain specific. So for particular disciplines or institutions like museums or archives, there are those for different functions like copyright, technical information. Often these things overlap and different schema or data structures are mapped or crosswalked or combined. I hope this makes a little clearer that when we talk about things like silences in the data or biases in the data, we're often thinking about what decisions were being made at the stage of the data structure level, what elements to collect for the data set, like title or date, creator, etc., and what things maybe weren't saved, like rebirth or death dates or gender, places one traveled or life partners or any of those kinds of things, right? Those decisions are built into the standards that we use or don't use. So again, it is worth it to do the deep dive early on as you start the project. When constructing a database, especially for research or digital humanities projects, for example, linked open data and standards play a crucial role in interoperability, sustainability, and usability. So here's why they matter. Just very quickly, like databases rarely exist in isolation. Linked open data allows, or LOD, standing for linked open data, allows databases to talk to each other using shared identifiers and vocabularies. Examples of this are like digital humanities project on historical figures could use Wikidata or Library of Congress name authority file or Getty vocabulary, like the Getty vocabularies of either Union List of Artist Names, ULAN, or TGN, the Thesaurus of Geographic Names, for richer contextual information. And you're not having to reinvent the wheel. You're not having to come up with those things yourself. You're pulling from authority files that have already done that work for you. And again, this enables cross-referencing and making the research just more comprehensive. Standards. Following metadata and ontology standards ensures that data is structured, discoverable, and reusable. So these are standards like Dublin Core, which is a general metadata standard for documents and archives, CDOC CRM for cultural heritage and museum databases, or RDF or Sparkle for querying linked data. So long-term accessibility and preservation, proprietary databases, private spreadsheets, local systems risk becoming obsolete if they don't follow open standards. Linked open data and standards help sort of future-proof data for long-term access. If you're not familiar with the FAIR principles, FAIR standing for findable, accessible, interoperable, reusable. These are key for research databases. So for example, a historical database stored in a CSV format with no shared standards might not be usable in 20 years, but a database built with RDF and linked to Wikidata could still be accessed and understood. Structures like linked data enhances searchability and AI-driven analysis. And then finally, different fields, it's history, linguistics, environmental science, can reuse and build upon existing data sets if standards are followed. So it does support multidisciplinary research. I know we're running low on time. If you all can't stay, I completely understand. I will actually quickly skip ahead to sharing a survey, and then I will go back to if you do get a chance, and this will also be sent out in an email afterward, but if you do get a chance, we always love to get feedback on how we're doing, what you think of our workshops, if they're useful to you, other concepts that you'd like covered. So I am going to put that in the chat along with a link to Ryan's workshop next week in case you're interested. So please, if you have a minute, fill out that survey. And while you're doing that, I'm going to go back and talk a little bit about ethics, legacy data, and access just to wrap up. So if you can stay with me, great. If you can't, completely understand. So when we talk about databases and the impact that they can have, it's really important that the ethical issues are addressed at the outset of the project, and that questions like these remain at top of mind throughout the project's lifespan. Again, these are pulled from Johanna Drucker and her great book, but they're just wonderful questions to ask yourself throughout the project. Knowing where your information comes from and thinking critically about the sensitivity around who your data might affect, right? That's really important work. I also want to pull again from Drucker to talk about legacy data and its challenges. So while many humanist records of great antiquity can be considered quote unquote data, they have to be remediated to become digital data and computationally tractable. Examples such as quote unquote legacy data sets, or I should say examples of such legacy data sets are things like the Roman census records, inventories of monastic libraries, and the lists of settlement records in Iceland. These can be, and many have been, put into digital form for study and analysis. Another type of legacy data that would be of the sort made digitally for an unrelated purpose or project is being used for research. So an example here, King's College London, which has long been involved in digital humanities research, took on the challenge of assessing the data inherited from early three decades of the project, or earlier 3 decades of the project. While this does not sound like a long time, the period has witnessed considerable changes in practices of digital methods. The group identified about 100 legacy projects that spanned a wide spectrum of text analysis and annotation tools, digital corporate text, images and musical scores, to digital editions, historical databases, and layered maps. The team decided to collect considerable information about the project, so about the various projects. So team members, funding, period of time in which the project took place, standards that were used, and other details. And among the difficulties addressed were the security breaches that had occurred on unmaintained applications. Another issue was managing expectations of various team members, particularly in situations where partners from different countries and institutions were stakeholders. Preserving data and metadata in a variety of formats is expensive, but without the original interface, it may be illegible or unusable. Some of these concerns will come into focus, as you think about sustainability of a project. But for researchers using legacy data, there are some other concerns. Data made for specific research projects is often idiosyncratic, may not be documented. The quality control on data production may have been uneven. Legacy data issues are particularly complex in medical, humanities, and social science fields, where the possibilities of violating original agreements about collection of information might be at risk of being broken for new projects. Any identifying information that can be, quote unquote, re-engineered could put human subjects at risk and violate their privacy. In addition, monetizing any data in a use for which it was not originally intended poses an ethical issue. And then finally, legacy data often do not reveal the process by which they were modeled necessarily. So what was eliminated in the process and what was conflated? These are the questions that you're left with. Data have potency and appear to have an authority as a statement of facts. And so knowing their source and their history is crucial. And being as transparent as we can about that is, I think, essential to these types of large database projects. So to wrap up here, when picking tools and building databases, it's important to think about access. And I think we need to challenge the assumption of full transparency, right? That everything in a database, every part of the research has to be exposed. Not all data should be fully accessible to everyone all the time. Different cultural and ethical and legal considerations may and probably should limit access. Granular control of data retrieval access and use is necessary. And that's why, these things like SQL can really help us control what data gets brought up when. There are also cultural considerations in terms of data access, right? The Mercurtu platform is a great example of this, right? It was developed for Indigenous communities to control access to their cultural knowledge, and access may depend on role, class, position, age, gender, certain kind of knowledge, right? Or kinship groups. It's a one-size-fits-all model does not work for all communities. So again, this is why we may choose to restrict access to our data. And then there are also, ethical constraints. So privacy concerns, student records, personnel files, health data must remain confidential. It may be important to anonymize your data, and database systems can help us do that. Consent is also really important, right? Personal data should not be shared or monetized without prior permission. And so certain staff or researchers may need to have access to certain kinds of data. This happens a lot in the medical field, but others may not see that kind of data, right? And you have to be able to limit who can see what when. And again, researchers must consider the risk of misuse or harm. And this is why we have people go through IRB when they're building databases. These projects do have to be evaluated on those levels for human harm. And then the digital divide, right? Does digitization promote inclusion? Or does it reinforce disparities? These are always questions that we have to ethically ask ourselves when doing this kind of work. Then again, intellectual property and data ethics. Who has the rights to get into the intellectual property? This always has to be negotiated and not just assumed. Digital assets risk being appropriated or misused once online. So again, always trying to make sure that credit or citation is part of what we do. And data structures should incorporate different levels of permission to protect rights and ownership of folks. So thank you for sticking around a little after. If you have any questions, I'm happy to answer. Again, I'm going to put the survey in the chat. And I also want to share here that so much of what I've shared today has come directly from Johanna's work. And so please take a look at that. I can't recommend it enough as a resource. Also, if you want to learn more about SQL, W3 Schools is a great place to start for that. Thank you all. Questions?